We want to approach our AC circuits with a slightly different mathematical description. So suppose we have a circuit element. Here's our element. And in that box could be a resistor, it could be an inductor, a capacitor, any combinations of those in series or parallel. And we have some type of voltage source. And we want to get that current response. Now, when we write our voltage source, sometimes we write it in terms of signs. But in this case, we're going to write our voltage source as V naught cosine of omega t. And our current response we'll write as I naught of cosine of omega t minus a phase constant. Now remember, the I naught and the phi are both functions of omega. Now keep in mind that we have our Euler formula where I of an angle, which we'll call omega t, can be written as cosine of omega t plus I sine of omega t. So now what we're going to do is complexify our voltage and our current. And we'll write these as complex functions. We'll write them as voltage of t. And sometimes people write it complex, but we can eventually drop that notation. We'll write it as an amplitude times e to the I omega t. And we'll write our complex current as I naught e to the I omega t minus phi. Now remember, this is equivalent to I naught e to the I omega t e to the I minus phi. Now, eventually, we want to take the real part of the voltage. And when we write this as a complex number, what we're taking is the real part of the complex function e. So we'll write it as cosine of omega t plus I sine of omega t. And the real part is just the cosine. So that is V naught times cosine of omega t. And in a similar way, the imaginary part of this voltage is just V naught sine of omega t. So whether we write our voltage as a sine function or a cosine function, we can still use this formalism. Now, what we'd like to do is describe the current response in terms of a complex number multiplied by the current to give us our voltage. Now, I'm going to drop the complex c, but remember these are complex functions, and I want to introduce a quantity z times the current. And this number z, this complex number, this is a complex number. We can think of that as some number x plus iy. And, or more importantly, we'll think of z as a modulus and a separate phase, writing a complex number as a modulus and a phase. And this is called the impedance. Now, let's just solve our problem. If we know this, so if we know z for any combination of circuits, then we can write our equation as V naught e to the I omega t. Remember, this is where the time dependence is, times the complex number modulus e to the I delta times the current response, which is I naught e to the I omega t times e to the minus I phi. And now, in order to make the equality work, for one, you can see that we can divide through by e to the I omega t. So our first step is V naught equals the modulus times I naught times a complex phase times another complex phase. Now here, V naught is a real number, the modulus is a real number, I naught is a real number, and we have two possible complex numbers here, so the only way this equation can work if this combination is equal to 1. And what that means is that the phase of the impedance, delta, has to be equal to the phase that we're trying to find in the current response. Because why? Let's just make sure that e to the I phi times e to the minus I phi is 1. So not only have we solved for the phase if we know z, but now, because this quantity is 1, our other key quantity that we wanted, which was the amplitude, I naught, we can write that down as, let's just put it over here, I naught is equal to the amplitude of the voltage divided by the modulus of the impedance. And so if we can write down the impedance as a complex number, then we can solve our problem of finding the current amplitude response and phase response. Our next step will be to understand how to find z for any combination of circuit elements that are either in parallel or series by circuit elements, resistance, inductors, or capacitors.